Good afternoon. Our next speaker, Dr. Eric Davis, is a senior research physicist at the Institute for Advanced Studies at Austin in Austin, Texas, which is the basic and applied research division of EarthTech International Incorporated. Since 1984, Dr. Davis has been a contractor and or consultant to the United States Air Force Research Laboratory, Department of Defense, Department of Energy, and NASA. From 1996 to 2002, he was the director of aerospace physics at the National Institute for Discovery Science in Las Vegas, Nevada. His professional research includes beamed energy propulsion, directed energy weapons, the quantum vacuum and faster-than-light propulsion, flight science. Dr. Davis is the co-editor and author of the peer-reviewed academic research monograph, Frontiers of Propulsion Science, published by the American Institute of Aeronautics and Astronautics Press in 2009. He also authored and co-authored numerous Air Force and Department of Defense technical reports, peer-reviewed symposium and technical journal papers, chapters in books, and conference papers. He earned his PhD in astrophysics at the University of Arizona in 1991 and did his graduate work on the Voyager 1 and Voyager 2 missions to the outer planets while at the Lunar and Planetary Laboratory and the Department of Physics. Dr. Davis is a fellow of the British Interplanetary Society, associate fellow of the American Institute of Aeronautics and Astronautics, member of the New York Academy of Sciences, member of the Directed Energy Professional Society, and member of the American Astronomical Society. He is on the international editorial board of the Journal of the British Interplanetary Society, an advisory board member of the Tau Zero Foundation, a member of the 100-Year Starship Study Science Advisory Board, and a member of the Icarus Interstellar Technical Advisory Board. Dr. Davis has appeared in or contributed to many American and BBC television and documentary film projects, as well as many popular science news articles on interstellar flight and faster-than-light propulsion. Safe to say he's highly qualified. Let me welcome to the stage Dr. Eric Davis.
Thank you very much. And my next television appearance is going to be on the Sci-Fi Channel next month on Joe Rogan Questions That in mid-August or late August, so be looking for that. I don't have the exact date. Anyway, let's get the slides up here. Here's what I'm going to be talking about. I'm going to be taking you on a tour of interstellar flight. What's it about? Who's doing it? Why? Why should we care? Why interstellar flight? Interstellar flight organizations, the Transgalactic Travel Guide, and advanced propulsion limitations. Then I'm going to give you Einstein's ground rules for relativity. I'm going to make you all warp drive experts in 2 easy lessons. So then we'll wrap that up with my discussion on FTL space warps in all their glory. I'm basically going to run you through all the research I've been doing in the last many years since I began working for Hal Puthoff in Austin in 2004, and then the conclusion. Okay, why interstellar flight? Why go there since we haven't gone out into the solar system and colonize it? Well, basically the human race is subjected to multiple existential threats in the form of extinction events. You've got climate change, you've got geological disruptions of well-known volcanoes, supervolcanoes, earthquakes. Climate change is beginning to rear its ugly head in a variety of ways. You have man-made disasters like nuclear, biochemical warfare, industrial accidents and contamination. And then you're going to have lots of outer space threats out there that we're beginning to become more familiar with, among which are the solar coronal mass ejection. You have the Carrington event back in 1859, the Hydro-Quebec electric grid that took place in 1989 that shut down the electrical regional power in Quebec. Electrical infrastructure and satellites are destroyed whenever a gigantic solar flare hits the Earth, and it hits it at the right angle, at the right latitude, and in a way that the Earth's magnetic field is not able to prevent it from striking the Earth and shorting out electrical systems. We're subjected to asteroid and cometary impacts. We've got craters all over the Earth that represent the impacts that have been going on since the Earth was born, among which were the, if I can see it here, is the Yucatan Peninsula crater that is said to have led to the extinction of the dinosaurs 66 million years ago, the meteor crater in Arizona 50,000 years ago, Then we had Tunguska, Russia in 1908, which flattened millions of square acres of forest out in deep Siberia. And then you all know what happened when Comet Shoemaker-Levy went to Jupiter in 1994, and several pieces of the comet broke up and splattered all over the equatorial region of the planet. And then we had Chelyabinsk, Russia last February, 1,200 people injured, more than 600 children. You know, this doesn't impact the human race very much, but we have not, our modern record of what happened hundreds of thousands of years ago is very incomplete. We don't have a complete history of human life back in the ancient days, going back a couple million years when our species first arose. So we don't know what happened to people back in those days. They were awfully subjected to asteroid impacts and cometary impacts on the Earth in conjunction with the geological disasters. And then the last thing, ET alien invasion, you never say never. You never say never. I mean, it's just a mistake to basically think that aliens will never, ever come to the Earth and want to invade. You just don't make that mistake, because we have the Spanish to thank for what happened to North America when they came over here and discovered America. Let's see, the next thing. Okay, so in thinking about those disasters that could potentially befall us, we have the potential for the expansion of mankind into the solar system. And right now, we're just barely touching the moon and Mars. And in order for us to survive as a species beyond the period of which we may evolve out of our existence, I guess, in other words, perpetuate the species further, the best thing to do would be to move out into space, to think about colonizing space and spreading mankind out into habitable environments. However, we find that Moon and Mars are not very habitable, but they're very rich in high-value resources. However, for man to live on the surface of the Moon and on Mars, they're going to need a lot of infrastructure to support astronauts. You have to shield astronauts against the effects of galactic and solar radiation. However, by moving out to the Moon and on Mars, you can support dramatic new development in space industry, expanded economic development, new high-tech jobs, and you'll create new technologies and create new investments and wealth. So there's a real good business reason, a good business model for going out to the Moon and Mars. And it may not be necessarily to colonize, but it may be for the purpose of mining the resources on those bodies. And one thing I didn't put on here was asteroids. Asteroids also fits into that picture. Now, the outer solar system is really too hostile for human existence. It would be an incredible stretch to create the kind of habitats necessary to support mankind in those radiation environments. They're far, far away from Earth. Resupply missions would take years. It would just be too difficult to live out there. However, again, the outer solar system is rich in high-value resources. Astronaut infrastructure, as I said, radiation shielding requirements would increase dramatically out there. However, once again, if we can push out beyond the asteroid belt and start mining resources out in the outer solar system, like out to Saturn's moon, Titan, and a couple of the moons around Jupiter. I'm thinking of maybe some of the moons around Uranus, and then a lot of the asteroids, of course, in between Jupiter and Mars. You can then, once again, you'll have a business model for space industry, expanded economic development, new high-tech jobs, technologies, create new wealth, and whatnot. The parameter space to develop the solar system is rather limited, and it's limited because of the infrastructure to keep humans safe and protected. And the answer that's usually given by the space scientists is, well, why not just keep people on Earth and let robots do it? Well, it doesn't work. We've been finding out that robots have significant limitations to their abilities to work on other bodies. They work well, they work beautiful, they actually are well engineered, they can last longer than we originally engineered them to, and we get a big return on the amount of money that we invest in them as taxpayers. But the problem is you can't replace a human in an environment. That's very difficult, requires intuitive thinking, requires thinking on your feet, leaps in logic, and it requires the things that you can't program into a robot. Now, why would we want to go into interstellar space? If we can't live out really in the outer solar system and the Moon and Mars are going to be marginal to support mankind, well, here's a good reason to go out into the galaxy. So far, the exoplanet searches as of June of this year show that we have 893 planets in 656 or 696 planetary systems, 133 multiple planetary systems which are similar to our solar system, and 262 may actually be habitable planets. They'll be Earth-sized, they'll be super-Earths, like about the size of Neptune and Uranus, and Mars-sized. And then the nearest exoplanets within their habitable zones around their parent star, where habitable zone means where water runs like a liquid. It's in liquid form. Well, that would be about 22 light years away, given the latest discoveries. There are greater than 18,000 total planetary candidates identified to date, but they haven't been evaluated yet. And the statistical analysis on all this shows that at least one planet on average orbits every star in the galaxy. Now, that's just the average. That implies that there's an estimated 100 to 400 billion planets in the galaxy, and 17 billion of them are Earth-type planets, and many more exoplanets are freely floating. They don't have a parent star. They're just orbiting the center of the galaxy right now. So the total number of planets that we can estimate now is that there are more planets than there are stars in the galaxy. This is really an excellent reason for really pushing mankind out of the solar system and into the galaxy. Basically, we have a lot of latitude. The parameter space for exploration, for colonization, now becomes literally infinite. And again, that business model will still be supported. We can have a business model for colonization, space industry, expanded economic development, high-tech jobs, new technologies, new investments, and wealth. So it'll be a wonderful thing. Okay, so who are the interstellar flight organizations that are looking at this possibility of going into interstellar space? And we have a nice list here. It's actually more than anybody here probably ever thought of. The first was formed by the British Interplanetary Society in 1933, and they are now 80 years old. And I'm a fellow of the British Interplanetary Society, and they have several publications and a peer-reviewed journal. And that was co-founded by Arthur C. Clarke, his brother Fred, and a number of other UK rocket scientists and engineers back in those days. The Planetary Society came along in 1980 and was chartered by the founders of the JPL and all of the Mars mission scientists. Carl Sagan was one, Louis Friedman. Then the SETI Institute came along in 1984. 1984, and that was John Billingham and Jill Tarter, Jill Tarter and Frank Drake and others. And they are, that's the Search for Extraterrestrial Intelligence, SETI. And their purpose is to establish radio observatories all around the Earth and listen for alien signals. Okay, then the International Propulsion Society was a short-lived organization in the 90s, and it was later resurrected by Mark Millis, who was one of the co-founders, and Mark Millis was the Breakthrough Propulsion Physics Program Manager at NASA Glenn. He founded the Tau Zero Foundation and the Centauri Dreams blog site, which is like the news reporting site for everything interstellar, and that was founded in 2006. And then there's Faces from Earth in 2006, Global Starship Alliance in 2011, and I don't know much about those organizations. Icarus Interstellar was born in 2011. It was an outgrowth of Project Icarus. Project Icarus was son of Daedalus. That's what Icarus is. Icarus is the son of Daedalus. Project Daedalus was founded by the British Interplanetary Society in the 70s to study the possibility of building a fusion-powered rocket to explore Barnard's star, some many light years away. And that study was done after 5 years, and then it languished because the NASA space program kind of languished, and the space shuttle kind of dominated all of what we were doing in the 1980s. So we did not go to the stars, we did not go to the outer solar system other than for the robotic space probes that we launched. So basically, Icarus Interstellar is resurrecting Project Daedalus. And Project Icarus is looking at doing a fusion rocket in modern times using 21st century physics and 21st century technology. Then DARPA formed the 100-year Starship study in 2012 with a $500,000 seed funding, which was awarded to the Jemison Foundation for Excellence, Icarus Interstellar, and the For Enterprise Development Foundation. Then DARPA also awarded $500,000 to Space Gambit, and I have no idea what they do. They have a website up, and they really don't have a lot of information on it. Space Colony Earth came along in 2012. I think they've gone defunct. They haven't been doing much of anything. And then the Institute for Interstellar Studies in 2012. All these organizations, most of these organizations popped up in the last couple of years because of the DARPA-NASA initiative to start focusing on looking long range out 100 years into the future and thinking about what it will take to develop the science and technology to build a starship in the 22nd century and launch it in 2211. And that's why these organizations were all born. All right, to get a feel for what's going on as far as traveling through the galaxy and what distances are involved, what energies and how propulsion physics can play into all this and what its limitations are, we've got to look at the Transgalactic Travel Guide. So I'm going to take you on a tour of the galaxy really briefly here. Measuring the distance from our sun, we start at the Earth, which is located at a distance of 1 astronomical unit from the sun. The sun would be out here somewhere. And this is a log scale where every increasing increment increases by a factor of 10. 1, 10, 100, and 1,000 AUs. And basically, we're going to start at the Earth and extend all the way to the diameter of the galaxy right there, which is 100,000 light years across. And we're going to increase the distance scale by factors of 10. This is the basic unit that we measure distance in the solar system as factors of an astronomical unit. All right. When we go further out beyond the solar system, the astronomical unit becomes inconvenient. It's too small. Then we've got to switch over to terms using, or units of measure using light years. That's the distance that light travels in 1 year. That distance, I don't remember what it is in meters, but it's 6 trillion miles. Okay, so that's how far a light year is. The distance that light travels in a year sounds like it would cover a lot in 1 year, but in space, because space is so big, light speed is really slow. Like, for example, to cross the entire diameter of the galaxy, it'll take a beam of light 100,000 years. All right, so here's the edge of the solar system, roughly just inside and outside of 100 astronomical units, right there. And the edge of the solar system is where the effects of our sun meets the galactic background. It is not a distinct distance, but is rather comprised of several distinct layers, beginning with the terminator shock at 75 AU, down to 80 AU, and it blends in with the heliosheath at roughly 90 AUs, and then that blends in with the heliopause at 100 AUs, which is where the Voyager 1, I think, is now, maybe it's Voyager 2, are located now, and the heliopause goes out to 110 AUs. And then out to 170 AUs is the bow shock. That's where the magnetic field of the sun reaches out to its maximum extent, and it's ramming against the gases of interstellar space as the solar system orbits around the center of the galaxy. So that magnetic field is pushing against that gas, and that's why we call that a bow shock. Okay, then we have, on the outside of all that, we have the Oort cloud. And the Oort cloud is the origin of where we think most of our cometary material comes from. And that ranges from about roughly 0.1 to 1 light year. And as you see, we have the log scale here in light years now. Now, the nearest star system is Alpha Centauri A and B, 4.3 light years. And then star C is Proxima Centauri, which is at 4.2 light years. And so that would be indicated right here on the light year log scale, right there, about 4.3 light years. Now, the nearest habitable planet, given what I just showed you earlier, it is not yet quite known where the nearest Earth-like habitable planet will be found. But preliminary estimates suggest that the location of habitable planets might lie within this probability distribution calculated by my colleague in Italy, Dr. Claudio Macconi. And it looks like it peaks just around 70 light years away. So now the reason why that this distribution is broad like that represents the fuzziness in our knowledge of exactly where a habitable Earth-like planet is really going to be. It's going to lie somewhere in here. And as we gain new knowledge from the Kepler space satellite and discover more habitable planets, we'll be able to tighten that band up and get a better measure. The nearest extraterrestrial civilization, are we alone in the galaxy? And if there are other civilizations in our galaxy, are they even farther away than the nearest stars, or could they even be closer? Provisional guesses suggest that the location of the nearest, where the nearest ET civilizations might lie, would be within this rough band, which is peaked at just a little bit shy of 2,000 light years away. And so thus this band is out here, running from roughly several hundred light years out to about 10,000 light years distance. We just don't know yet. Until we actually make contact with ETs out there, we'll get a better idea of where they're located. Okay, so this is the transgalactic travel guide, and here now we have the logarithmic scale on time, starting from a week, month, year, on up, all the way up to 100 million years. And this isn't the logarithmic next step. This is halfway up above that, and that's the 5 billion year mark. That represents the age at which we expect the solar system to die, when the sun dies and the solar system is gone. Now, here's what's interesting about this. If you want to understand how long it will take you to fly out to any of these interesting locations in the galaxy, you're going to have to decide how fast you're going to go. What propulsion system, what propulsion physics are you going to have to help you get there? And so we draw these diagonal lines like this. And these represent fractions of the speed of light. And here is the speed of light right there. Okay, now the present Voyager spacecraft are moving at 0.00006 times the speed of light. The next line below it is 0.0001, and the next line here is 0.001, and then 0.1. There's 1/10 the speed of light, and that's the speed of light. Now, to get an idea of how long it will take you to get to one of these destinations at any one of these chosen speeds, all you do is just choose your destination. So let's say we're going to go to Alpha Centauri at 4.3 light years, and at the speed at which Voyager 1 or 2 are moving right now at 0.00006 times the speed of light, now move left. And you'll see it's going to take, from here, I can't see it very well here because it's blurry. It looks like it's about 10 to the 5, 10 to the 4. It's going to take about 100,000 years. Okay. So it's going to take 100,000 years for Voyager to get out to the nearest star systems right there. And if you go faster, if you have a rocket that'll get you there faster, let's go at 0.1c. Then if you want to go to Alpha Centauri at 0.1c, you're going to go down here and you're going to go left, and it'll take you just several decades to get there. And if you can move at the speed of light in some kind of a photon rocket, then you can go from here down to there, and you see at the speed of light, it'll just take you several years to reach 4.3 light years. And of course, the farther away you go at the speed of light, the longer it's going to take you to get to the farther destinations. If you want to go faster and get to these destinations at shorter time periods, then you're going to need to be in this region. And that's the region where you're going to need a breakthrough propulsion physics that'll jump the light speed barrier. Okay, very quickly, this is the three-dimensional chart just to give you an idea of how the Newtonian rocket equation really constrains rocket technology, even advanced antimatter rockets. How much propellant? This is the propellant required to fly a space shuttle orbiter out to Alpha Centauri at 4.3 light years. This axis is the propellant mass that you're going to carry in the fuel tank. And you see it's 10 times the orbiter here, and it goes up to the number of supertankers, the mass of the Earth, and the mass of the Sun at the top. Now, on this axis, you're going to have the better rockets. That's the rocket efficiency measured by specific impulse. Specific impulse has units of seconds. That's not units of times. It's just the mathematical units work out so that you have units of time in seconds. So the Orion rocket is a pulse nuclear bomb where you have little miniature nuclear bombs going out the rear. They explode, and they exchange their momentum with the pusher plate. That pushes the rocket forward. The specific impulse is roughly a few thousand seconds. ICAN-2 is a hybrid antimatter fission rocket with a specific impulse of maybe about 10,000 seconds. And then here's a specific impulse associated with nuclear fusion rockets or advanced ion engines at 50,000 seconds. Okay, so then here's how you figure out what kind of fuel you're going to need. This is your flight time. So you start at 50 years, 100, and 500, and 1,000-year trips out to Alpha Centauri. So if you're going to take a 50-year trip out to Alpha Centauri using a space shuttle-sized craft, and you're going to use the Orion microfission bomb rocket, you're going to need to go up and over, and you find out that you're going to need the mass of the Sun in your fuel tank. So that's really hard. Okay, that means you're going to have the mass of the Sun in little tiny atomic bombs in the back of the crew cabin. All right, if we're going to talk about going with a high specific impulse rocket like 50,000 seconds, then basically that number is actually going to drop quite a ways. To get to 50,000 seconds, you'll go from here at 50 years right there, and you'll see you'll need roughly 10 times the orbiter's mass in fuel. So this is looking really good, but you're still limited by light speed. You can't reach the speed of light, and so you're still going to take 50 years. Now, if you take longer trips, Now, here's an advantage of the rocket equation is if you're willing to go multi-generational star flight, whereas you'll have an astronaut crew that'll take off, they'll reproduce, and every generation gets reproduced on a world ship, and they'll live out there for hundreds or thousands of years, you'll see that the fuel requirement is going to drop dramatically no matter which specific impulse you choose. And so once you go out in these 1,000-year missions, your fuel requirements begin dropping off and getting into more reasonable regimes. But still, this is a lot of fuel. Okay, so what kind of rockets can we have? This kind of chart actually shows you the type of advanced propulsion that we have available right now that's viable to do. You have electromagnetic catapult, the NERVA nuclear fission rocket, then you have the Saturn V, advanced nuclear electric propulsion. That's an advanced nuclear-powered ion rocket. Then you have an advanced fission fragment, fusion rockets, fusion ramjets, laser propulsion, and then an antimatter rocket. Now, how fast do those go? Well, just choose one and then go across horizontally to this axis, and that's their flight speed in kilometers per second. Or you can go on this axis, and this would be their flight speed as a fraction of the speed of light. So let's just choose a matter-antimatter annihilation rocket, the very top one, and its maximum speed is roughly half the speed of light. Now, if you want to find out how long it's going to take you to fly at half the speed of light using that type of rocket to any of these distances, now these are distances, stellar distances in the diagonal direction here. So let's say I want to go half the speed of light using an antimatter rocket out to 40 light years, and then how long will it take me to go out there? About 100 years. So you see, even with the best technology, we're limited by time, distance, and propellant, and the physics is limiting. So we need a breakthrough. We need to be able to jump the light speed barrier. We need to be able to have something to go beyond and outside of Newton's rocket equation. The rocket equation is really limiting. Okay, so before I get into warp drives and wormholes, I want to give you 2 easy lessons to teach you all how to be relativity physicists. And this will help you understand what I'm going to be talking about. First of all, Einstein published a special theory of relativity in 1905. It says basically no material objects can reach or exceed the speed of light. Absolutely. The speed of light is the universal speed limit. The speed of light's value is 300 million meters per second. That's also about 3 million football fields per second. So can imagine a running back being able to go out there at 3 million football fields per second to catch a pass. I don't know. That's pretty heavy-duty speed there. What this does is this sets up something called the light cones of causality. Einstein was working with the picture of space and time that had been invented right at the turn of the 20th century. And space-time were unified, and it was assumed to be flat. Space-time was as flat as the top of this podium right here. And so therefore, we have something called the causal structure. Cause always precedes effect. Or your future moves to your present, got it backwards. Your past moves to your present, moves to your future. Okay, so what Einstein said is relativity theory requires that all events, no matter where they're located in the universe, all observers, like you guys sitting in your chairs, no matter where you're located in the universe, or in this ballroom, for example, you all have a causal light cone attached to you. And right now, you're sitting at the now. That's the observer sitting right now in this event now. And this is the observer's hyperspace of now. And that hyperspace is 3-dimensional space that we live in. And the time axis, the time direction is vertically up this way. And space is horizontally perpendicular to the two cones right there. Okay, so let's look at this chart just to begin with. Okay, so, I'm going to go ahead and start with here. So basically, your causal structure of your past, your present, your future is laid out in what's called the light cone. All of your past activities, your past motion, your past trips, wherever you went, because you cannot reach or exceed the speed of light, your past events of everywhere you've been is always inside the past light cone. So your entire past is kept within this light cone here. And then you move up to the present time right now where you're sitting in your chairs watching me speak, and you're right here. And then everywhere you're going to go from this point on, after I speak now, and then after I give my speech and going forward into the future, you're going to be limited to motion in time and space within the future light cone. So your motion is on a line called a world line. The world means the entire history of your life. And that's a world line, and we call that a time-like world line because it goes in the time direction. Remember, time is vertical, goes up that way, and all three directions of space that you live in is this way, okay? So this is a world line, a time-like world line of all the events that you've ever done in the past, what's happening to you now, and what will ever happen to you in the future. Now, why they call that a light cone is because you notice this is the cone that swept out. Well, let's look at this diagram because it's a lot less confusing. Time is this way, space is that way, and all 45-degree angles with respect to the time and space axis is the surface of the cone, and the only things in the universe that live on that surface are light rays, electromagnetic radiation, hence light cone. So light cone represents the surface of which all light rays everywhere in the universe lives, on that surface, right here on that blue shaded surface. Light moves on that diagonal line, on that surface, and that's called the light-like world line, okay? So Einstein said, we set up a cause and effect, causality, attached to your light cone of past, present, and future, and therefore you have what's allowed, all of the different alignments of the light cones. The light cones of every observer everywhere in space and time are all aligned in the same direction. They have to point in the same direction. So you notice how the time axis is always vertical, and the space direction is always perpendicular, okay? So this observer, these observers here, they all are lined up in the same direction no matter where they're located. Now here's three observers or three events, and they are legally connected up along a time-like world line so that this observer can see this guy can see this guy. And so this is an allowed motion through space-time. You are allowed to travel through space-time on such a motion as long as you follow an aligned light cone path like that. Now, the perpendicular direction in the space axis is forbidden. That is because I said everything that moves at the speed of light lies on that surface. But what's outside here is forbidden. That's the spatial region where things go faster in light. And it is forbidden to go outside in this region and go faster in light. You can't do it because of Einstein's universal speed limit restriction. Okay, so that's what special relativity gave us. Well, then in 1915, general relativity comes along. There were problems with Newton's law of gravity. Newton's law was failing at the end of the 19th century. It was making wrong predictions about a number of astronomical things that astronomers were observing. And they were saying, oh, I make all these calculations of what I'm observing using Newton's laws and Kepler's laws of motion, and they're wrong. They were right for most of the planets, but now all of a sudden we're seeing some wrong stuff. And Einstein went back to the drawing board and he said, okay, maybe I can figure something out. Special relativity was a theory of constant motion, constant velocity, or relative rest. He did not include forces or accelerations, and that's the difference. So Einstein went back to the drawing board with relativity theory and he said, what happens if I include forces and acceleration in space-time? Well, a big startling thing happens. You warp space. You basically end up replacing Newton's laws of motion and gravity. All forces and accelerations are replaced by curved or warped space-time geometry. Picture space-time again as a flat surface, but it's more like a stiff rubber sheet. You put a heavy ball in it, or a bowling ball, or a lead ball in it, or even the planet Earth right there, and that heavy mass will bend the space-time around it. And you see that bending right there. See, the space is flat out here, but the Earth is rotating around, and it's bending space in because of its big mass. And because the Earth rotates, it's also dragging it. Think of space-time as like a rubbery sheet molasses. So when you have a rotating star, planet, or galaxy, that rotation causes space to drag around it. That's called frame dragging. So that's what Einstein discovered. What you think is a force, what you feel is an acceleration in your car or in a plane or in your emotion is not a real force and it's not a real acceleration. Instead, it's curvature. This curvature. This is the gravity that holds you on the planet Earth. There's this curvature right there. That's what Einstein discovered. And what's wonderful is it has special relativity theory already built in. It's very well tested. And here's the beauty of it. Because space can be curved, guess what Einstein discovered? The light cones of causality are not universally fixed for all observers. Some light cones can be tilted over with respect to other light cones in warped spaces. And so here's an example of the tilting. So here's the time axis. Here's the space axis. This is the space of forbidden motion, remember? This is the hyperspace that all of your three-dimensional space is in, and your present is right there at the point in between the two cones, the past and the future. And now curved space, I'm gonna bend space with some kind of fictitious mass. You can't see it here, it doesn't matter. But I'm bending space along these arrows. That's what this means. Space is curved around like that. So this observer here is going to observe this guy right there. And there's this guy right there at that point. And do you notice that his light cone is tilted over? It's really cool. His light cone is tilted over, and you notice his time direction is that way. His space direction is that way. But relative to this guy is almost moving at the speed of light. His position is such that this guy here is looking at him, and he's tilted almost 45 degrees. And remember, anything that's at roughly 45 degrees is moving at the speed of light. Now take a look at this guy. This guy is so tilted over, his future is pointed that way, his past is right here, and it goes that way, and his forbidden space region is this way. But look at this guy. This guy is looking at this guy, this first person right here is looking at that event or that person right there, and he says, wait a minute. His time-like direction, his time-like world line is pointing in the forbidden direction. That way. That means he's going faster than light. But wait a minute. Is he violating Einstein's light speed limit? No, because this guy's time axis is that way. His time-like world line is moving within the light cone. He's not violating light speed in his reference frame. In his reference frame, he is moving within the light cone. He is moving less than the speed of light. But this guy says, oh, that guy's moving faster than light, because remember, the light cone is tilted with respect to that one. And this one is another one where it's tilted almost in a 45-degree angle. This guy's future is going that way. His past is that way. So this guy sees him as going, wait a minute. This guy's future is up that way, right? This guy's future is down that way. Oh, this guy's going backwards in time. He's in a time machine. He's going backwards with respect to this guy. This guy is also going backwards with respect to that guy. See, this guy's future is that way. His past is that way. Now, he's moving in a time-like direction, right? You see, it's vertical with respect to him. So they're aligned. Their time-like directions are aligned, but the future is down for this one, and the past is up. And this guy is going kind of almost going faster than light. So that's how you go faster than light without going faster than light. You can break the light speed barrier, but relative to other observers who are not in a curved space-time. Okay, so now you've got the tools you need to understand warp drives and wormholes. Okay, Einstein's general theory predicts two types of faster-than-light space warps that give us that effect that I showed you of the curved space and the tilting light cones. First one is traversable wormholes, which were discovered by Kip Thorne and his postdocs and grad students in 1985 to 88 at Caltech. And warp drives, discovered as a solution to Einstein's theory of relativity by Miguel Alcubierre, who was then at the University of Spain, I can't remember now, Portugal maybe. Okay, I want to show you a little math, not because I'm going to melt your brains here, but I just wanted to give you an idea of what these things look like. That's Einstein's general theory of relativity, the field equations for curved space-time. This object here is called the energy momentum or stress energy tensor. That encodes the material properties of matter, like the Earth, you, chair, atoms, suns, and galaxies. So you put matter here. This is the matter that's going to bend space, and that's the Einstein curvature tensor. This is the quantity that measures the warping or bending of space. Remember what I said about warping? I don't have a piece of paper, but just take a piece of paper and bend it. That's warping, okay? I'm using that word synonymously with curving and bending. So warping or space-time curvature is represented there. This is the coupling constant. That's Newton's constant of gravity, the universal gravitational constant, and that's the speed of light to the fourth power. 8 times pi times g over c to the fourth power. Anyway, that looks like an elegant, simple equation. It's really not. It's 10 nonlinear partial differential equations with symmetry conditions and boundary conditions. It's a nasty mathematical mess, but it's a lot of algebra. So here's what Einstein's general theory says. You put a source of matter into space here, and output comes curves. Matter, curved space, and curved space tells matter how to move through curved space. Okay. Oh, I didn't talk about the last thing. Okay. Einstein's general relativity says for faster than light space-time geometries, to give you the space geometry of curvature that you need to make a wormhole or warp drive, requires a type of matter that's exotic. It's not like the type of normal matter that we're all made out of. And it turns out it's exotic because it violates some heavy-duty mathematical conditions that Stephen Hawking invented back in the 70s. We don't need to get into that. And the type of exotic matter is negative vacuum energy. No problem. We've got negative vacuum energy. Anything that has a negative energy density or a negative energy flux is predicted by quantum field theory, and it's observed in nature. Okay, that's the taxonomy of traversable wormholes. So these are the type of traversable wormholes that you can have. And this is how they connect up with things in space. You'll have connections through space, time, and universes. You have different throats. Wormholes can have a variety of different throat shapes, like those things here. And then wormholes can also be time machines. Warp drives. Well, warp drives, you have Alcubierre's original expansion and contraction of space. Then there's Van den Broek, who modified Alcubierre's warp drive to lower the energy requirement. I'll talk about that briefly. And then there's Notario's warp drive. Notario had a different warp drive, and I'll explain that when I get to Alcubierre's warp drive. And then here are the alternate quantum gravity models of warp drive. Sonny White at NASA and myself have a extra space dimensional warp drive. And then there's one by Richard Abusi, who uses Casimir energy and extra space dimensions to fuel a warp drive. And then Hal Puthoff and myself and Claudia Macconi have the polarizable vacuum model. And I'm not going to get into a lot of those because that's pretty heavy-duty stuff. This is the basic premise of Alcubierre's warp drive. Here's the starship. The space-time grid is flat here around the starship. He feels no forces and no acceleration, no curvature. So he's going to feel the bubble of negative energy, some sort of negative vacuum energy. And that bubble is going to contract all of the space going out to the destination star, light years away, and it's going to push back all the space behind him to push the Earth farther away. And that's how you're able to go faster than light without going faster than light. This guy's not moving. He's sitting in flat space at relative rest. He isn't moving, doing anything. It's the warping of space here and here that's moving him. It's like a surfer on a surf, and the wave of the surf is carrying him toward the beach faster than light. Whereas if he was swimming through the water, he'd be limited to the speed of light, and he'd be spending a lot of energy kicking his arms and legs trying to swim to the beach. Where here, the surf on the wave is going to be pushing him faster than light. So that's how that works. And here's another representation for the Alcubierre warp drive. Here, space is flat. There's no curvature. Here's your starship. This represents the volume of space that's collapsed from your location to your destination star. This represents the volume of space from you to your departure planet, like Earth will be there, that you're pushing away from you. And that's what that represents. A traversable wormhole, this is called the Flam diagram. And what it shows you is regular space-time right here, right there. And here's point A, and here's point B. And a light ray is going to move at the speed of light, departing from point A, and it's going to have to go all the way through normal space-time to get to point B. That's going to take a heck of a long time, because remember, space is so big that light speed is slow. So if distances are measured in light years, it's going to take light years, years for light to reach those. Well, a traversable wormhole says, let's take negative vacuum energy, and let's create a shell of it around a location, open up a throat, push space open to form a throat, and thus you have the throat of the wormhole. And instead of going this way, you're going to go through the wormhole, and it's like a hyperspace tunnel, a shortcut from point A to point B, and you bypass all this distance and all the years you have to travel. Instead, this could be a matter of a few days or a few seconds of trip time, and you've effectively moved faster than light. You might put on a rocket on your back, or you might walk through here at 30 miles an hour, and you will have traversed this entire 10 light-year distance in a matter of a few days or a few seconds. So even though the guy going through the wormhole did not go faster than light, he didn't reach the speed of light. He's just walking through, or he's got a rocket backpack pushing him through. He's going to be going at a slow speed. But to everybody out here, they're looking at this motion occurring, and they're going to measure him with their clock saying, wait a minute, he just jumped 10 light years in a matter of days or hours. So he went faster than light from their viewpoint. That's because the light cones are tilted with respect to here and here. So this is what a spherical wormhole looks like. If that's the sun in the background and a throat is opened up, there's a negative energy shell around here. You would see a galaxy shrunken and distorted. It's inverted. You'd be looking through. It's like an inverse magnifying glass. Here's a Stargate opened up in Times Square. This represents the Stargate solution where the wormhole is not spherical. It's got a flat door-like opening. And here's another version of the flat door-like opening there. And that's the Stargate solution. What it means is the negative energy, the negative pressures and stress are all zero in that particular case. All right, so I talked about negative energy. So what are the negative energies? Well, here's the taxonomy of exotic matter according to nature and quantum field theory. So there are all the forms of negative energy, and this is really heavy-duty physics here, so I won't get into a lot of it. But let me just say that the yellow objects here that are identified in yellow, those are observed in the lab, or we see it in nature somewhere, or it is expected to occur but is not yet observable, but it has measurable consequences that you can observe. So these are the types of negative vacuum energy or exotic matter that we have in nature. And here's the Casimir vacuum energy associated with the Casimir effect, and here are the ones that we also realize. Anything in red is fictional. It's theoretical speculation. All right. Now, to talk about how much energy does it take to power these things compared to all the propellant you have to put in a space shuttle to move it to Alpha Centauri, or all the propellant to move into an antimatter rocket or a fusion rocket, we've got to look at the reality of what the energy requirements of warp drives and wormholes are. This word total is a mistake. That's an error I didn't catch in time. This should say net negative energy to produce a spherical traversable wormhole. Our throat is the diameter of the radius. You can take your choice. The energy of the wormhole is negative. Remember, I said it's negative. 10 to the 44th times the radius of the wormhole throat, or the diameter of the throat. That's nasty. And that doesn't make it look as much better as an antimatter rocket or a fusion rocket. Now, for a warp drive, it turns out that is the total energy. The total negative energy to produce a warp drive is going to be given by the warp speed of the bubble. It's surrounded by a bubble, and that bubble has a dimensionless warp speed. It's a fraction of the speed of light, like warp 1, warp 2, warp 3, so forth. R is the radius of the warp bubble, and sigma is the inverse of the bubble wall thickness. So that's the negative energy. Negative 10 to the 44th times the square of the warp speed times the square of the radius of the bubble times the inverse thickness of the warp bubble wall. That's nasty. That's a lot of negative energy there, and I'm going to show you some numbers. General relativity constrains warp speed to be less than or equal to this number given here. M ship is the mass of the starship, delta is the thickness of the warp bubble wall, and R is the radius of the warp bubble wall, of the warp bubble. It just says that and there's a condition that the net total energy stored in the warp bubble cannot be greater than that contained in the starship itself. That's to maintain energy conservation. Okay, so here's the bonfire of the realities. Now I'm going to take those negative energies of a wormhole and divide it by the speed of light squared. That'll give me an equivalent negative mass. I want to use an equivalent mass to show you the comparison of how bad the magnitude of this negative energy really is. For a wormhole of a radius of 1,000 meters, you're going to need negative 710 times Jupiter's mass. Equivalent. Remember, it's really energy, but I turned it into mass units. For a wormhole of 10 meters diameters, it's negative 7 times Jupiter's mass. And for 1/100th of a meter, 0.01 meters, your wormhole energy requirement is going to be negative 23 times Earth's mass. So here's Jupiter's mass in kilograms, here's Earth's mass in kilograms. And this is really ugly. Warp drives. Okay, well, it's even bad for warp drives. Here's the warp bubble speed, the speed at which the warp drive is relatively moving with respect to non-moving observers. So you got warp, 10 to the negative 5, 10 to the negative 4, 0.01 warp, 0.5 warp, warp 1, warp 2, warp 10, and warp 100. Those are fractions of those are multiples of the speed of light. Take a look at the energy requirement. Look at the size of those numbers. Negative, all of those are negative, of course, and look at the power on the 10 and compare it with the positive mass energy density, the total mass energy of the sun in joules. That's in joule units. This is pretty bad. So what do? Well, there's some options. And I didn't mention one thing about wormholes. reason why I said that was net energy, not total, is because the total energy of a wormhole can be positive, 0, or negative, depending upon how it's constructed. And I showed you an example of a zero-energy wormhole. That's the Stargate solution. Okay, so there's some alternatives. We have my colleague in Longview, Texas, Richard Abusi, got his PhD at Baylor on this. You use negative Casimir vacuum energy in extra space dimensions. This comes from superstring theory. And it turns out that if you apply that to a warp drive, you can get the energy down to negative, the equivalent negative mass of Jupiter. And that's a lot lower. That's about the size of a wormhole, of a wormhole energy requirement. However, these guys found that, Richard and his colleagues found that there's going to be a maximum quantum speed limit for warp drives. It'll be 10 to the 32 times the speed of light. That's 1 followed by 32 zeros times the speed of light. But for all intents and purposes, that's pretty huge, that's pretty big. Harold White, that's Sonny White, my colleague at NASA, we found a way, both of us, I gave him this idea to do the study, and he looked at taking the warp bubble and pulsing it at high frequency so that you can lower the energy demand on average, and you crunch all your energy into a peak pulse width spaced out in very short time intervals. That's what we do in directed energy weapons. That's how you create high-powered laser weapons. A laser like this is powered by batteries. This thing won't be able to produce megawatt power, but I could produce megawatts of peak power if it's pulsed up to megawatts, and the average taken over time is going to be very low energy. So he did an analysis of doing such a thing. He did high-frequency pulsing of the warp bubble. He shrank the thickness of the warp, he increased the warp bubble wall, and he made it thicker, and the result is that the energy of the warp is much smaller. And what's the equivalent mass of that energy? He found out that you could get it down to roughly negative 722 kilograms. That's something we can engineer. So we finally have a warp bubble energy requirement that's engineerable and doable. It's practicable. So this is pretty promising, and this is where he and I are doing our research right now to move forward. All right, so we're talking about producing negative vacuum energy. Okay, there are a variety of different ways of producing negative vacuum energy, and I'm only going to just review them quickly. This is called squeezed light, and it's a special form of light from a laser beam, and you put it through a lithium niobate crystal, and there's other kind of crystals you can use. And what it has the effect of is producing alternating pulses, the red pulses of positive energy, and the yellow pulses are the alternating pulses of negative energy. And if you have some kind of a fast rotating mirror, you can separate out the positive pulses and the negative pulses and concentrate the negative pulses right here, and that would be what you'd use to build your wormhole or warp drive with. Another way would be a series of, not 3, but a whole bunch of these photon emitters, and you'll combine all of their photons into a manifestly negative pulse of energy in a beam. And that's just a device that does the switching. We can't realize rotating mirrors like this. This mirror has to rotate once every 10 to the negative 15 seconds. But with the sodium gas cell, we can do an effective mechanical rotation electrodynamically here in the gas cell much faster than that. So this is how you would implement a rotating mirror. The Casimir effect. 2 plates, like a capacitor plates, block out the outside vacuum fluctuations in the quantum vacuum, and what's left is a reduced state energy inside the plates. And here the energy happens to be negative. And it's very weak, it's not usable, but it exists in nature. And we routinely make these in lab. This is a mirror. And if you take a mirror and you accelerate it rapidly through space, it will excite the quantum vacuum fluctuation and create a flux of negative energy. A beam of negative energy will be emanating from in front of its motion. And the best one that we've identified in the last 4 years is a parabolic cylindrical mirror, just like these that are used for solar thermal energy converters. The idea is that you put this in the vacuum of space, and it's going to focus all of the vacuum fluctuations that strike the mirror. They're going to focus along the focal line of the mirror. And Larry Ford at Tufts University did a calculation with his colleague Svader, and they figured out that the energy of the vacuum fluctuations that collects on that focal line is negative. And not only is it negative, it's astronomically negative. I had my student in Georgia Tech do a calculation of a micron size, a mirror the size of the width of my hair, and we produced like negative 10 to the 30th joules per cubic meter. 1 cubic meter of space contains negative 10 to the 30th joules. So we think we've got the way of producing warp drives and wormholes now. So this would be the way to do it. These processes are going to be weak and difficult to implement. This is really, the negative energy you get out of this is too weak to matter. Okay, if you're going to build a warp drive and a wormhole, you need to be able to detect the negative energy. It's like all radio engineers and light engineers. You have devices that detect the light, tells you how intense and bright it is, what its wavelength is. Or you have radio detectors, radio receivers, that'll tell you FM or AM radio signals, what the broadband wavelength is, and blah, blah, blah. Okay, well, we got to have that for negative energy, and we implement that using what's called a balanced homodyne detector, which were invented in the early 80s for the purpose of measuring the states of non-classical light. I'm just going to say basically it's, remember that previous graph, that previous thing I showed you, squeezed light? Okay, well, the balanced homodyne detector was specifically invented to measure this, to see the alternating pulses of negative and positive energy. And in fact, there it is. There's the raw data that was measured in the early 80s of positive, and the negative energy is in that little valley right there. Positive, negative energy, positive, and so forth. And this is called quantum tomography. It's like a CAT scan tomography, or positron electron tomography that medical doctors use to scan slices of your body tissue to hunt for tumors and damaged tissues. And so tomography can see this. And this is a squeezed vacuum state. There's the positive energy there, and the negative energy is this way. Well, the next thing that has not been done yet is doing a quantum tomography of the negative energy inside of a Casimir cavity. And that's what I'm working on with my coworkers at EarthTech now. The idea is to put two miniaturized nanoscale photodiodes inside of a cavity, about 1 millimeter on each side, on each plate, and the plates are separated by 1 micrometer, the width of my hair. And I want to make a measurement of the negative energy, and that's what it will look like. This is the computer model simulation of the actual of this version. This is the modified version of that. I'm not going to be able to implement this for this because they're two different systems. So I'm going to have a version of this here, and what it's going to give me is this. And these colored regions represent where the mathematics breaks down right there at stationary modes inside the cavity, and we're not going to be expected to see anything. But the negative energy is going to be observed here. If you insert the nanoprobes inside the cavity, this is how much the nanoprobes will disturb the transverse electric mode inside the cavity. Now that looks like a lot, but it's not. It's only 0.4% disturbance, so that's good. That's actually what we want. Okay, I'm getting close to finishing. This is the toughest problem that we have yet, and I'm not there yet. I'm still dealing with detecting negative energy and making negative energy, producing it and detecting it. We're nowhere near this. How do we construct a wormhole? We don't know how. I mean, Einstein's general theory of relativity, that equation I showed you, doesn't tell you how to do engineering. It just tells you how, it just says if you want to design space-time, you want to design curvature and warps, then it'll tell you what kind of matter you need on that right-hand side, that T tensor. Okay, and we know what that is, but it doesn't tell you how to implement it using technology. That's the problem. It tells you how to predict this stuff, but you don't know how to build it. So we can only speculate. Maybe just take a frame like this of Ford Spader mirrors. Maybe this is a line of parabolic mirrors all along here, and they're shooting negative energy down to create the spherical throat of the wormhole. And a spaceship just goes through that opening and goes right into the wormhole. Or maybe you might have an array of Ford Spader mirrors like this, and the negative energy is pulled off the focal lines, and they all concentrate at that little point there, and the rocket's going to have to go into that little hole in the middle. See, the idea, remember, is we got to thread a throat with negative energy in order to push space out, stretch it out, hold it open, and make that hyperspace shortcut so that you can dive into it and come out the other side. See, that's just a fictional diagram of what it looks like in 2 dimensions. Okay, that's what a FLAM diagram looks like. Warp drives, again, that's even more speculative. You know, that's the Star Trek warp drive engine from the Next Generation. Unfortunately, we don't know how to do that. We probably are going to have to do something similar to this with the Ford Spader mirrors. Okay, so let's assume we've already got our warp drive generator, our warp bubble negative energy generator, our detectors, our engineers have detectors. They can see the negative energy so they can locate it, shape it, position it in the right places, and we're all good and swell. All right, and now we can build the warp drive. Now what happens when you're going to start flying? When you start flying, you've got a couple pictures. You've got the observer's view. You guys are all the astronomers on the planet Earth. You're looking up in your telescope, you're looking up at the Milky Way at the night sky, and all of a sudden you see this crazy thing. All of a sudden your view is pinched off like this. And then this transition thing goes by you as it moves. And you see this distortion as this thing is transiting across your field of view. And then as it moves away from you, you see that. Well, that's what a warp drive looks like through your telescope. So that's what you would expect to see as an astronomer. If you're sitting in your starship, this is what you're going to see through your forward view window and your rear view window. And this is when you're at stop. You see the stars here and the stars there, forward and aft through your front and back windows. Now, if you're moving at 10 times the light speed, you notice how the stars now collapse down to those regions. And then if you're moving at 100 times light speed, the stars are now bundled up into little balls. They're blue for the blue Doppler shifting going forward and the red Doppler shifting going backwards away from you. For traversable wormholes, if you're inside that throat, this is what you're going to see. You can't navigate that. There's nothing to navigate with here. You're going to have all this distorted light. That's all going to be shoved around and distorted by the negative energy that's holding up the throat. Negative energy is gravitationally repulsive. See, all of us are made out of positive energy, like this, the atoms in our bodies and the floor and whatnot. That's gravitationally attractive. That's why the moon, the positive mass of the moon, and the positive mass of the Earth are gravitationally attracting. But negative energy is repulsive. It pushes things away, so light gets just pushed away into these distorted shapes here. Okay, well, we've come to the conclusion, so what do I have left to do? I've given you the grand tour, and right now, Earth Tech, which is my employer, we're looking at the critical technology issues, and we've started an experimental program to produce negative vacuum energy in large amounts. And what's important is the scalability of present technologies. Can we scale up negative energy generators that I showed you up to large sizes? Can we explore new ways to produce it? Are there other methods to produce negative energy other than the Ford-Spader mirror? Can we scale those methods up? And then we're going to look at the Ford-Spader mirror itself, the parabolic cylindrical mirror, and maybe even new advanced laser photonics to maybe find new ways to increase the amount of negative energy that a pulse laser can produce. Detecting negative vacuum energy, that's pretty much what I described was the balanced home dye detector in a Casimir cavity. That has not been done yet. After all these decades since 1981, when IBM first developed the balanced home dye detector, no one has measured the negative energy in a Casimir cavity. So I'm the guy who's going to do it. I didn't predict it. A colleague of mine who's he's a Polish physicist. He's a postdoc at the University of Duisburg-Essen in Duisburg, Germany, and he published 2 peer-reviewed papers describing the balanced home dye detector needed to do a Casimir cavity experiment. And I'm collaborating with him. I brought him out to Texas, and he visited with us over the 4th of July holiday in 2011, and we are working on building his experiment to test it. The next thing is to gain new insights by simulating FTL space warps. One thing is I told you about Einstein's general theory of relativity. That's 11 nonlinear partial differential equations, and the math is a bitch. So the best thing we've learned how to do this stuff is you can't do it by hand anymore. The calculations can take years doing it manually. The best thing to do is use computer simulation modeling. Throw this stuff into computer numerical algorithms and simulation modeling for visualization. And there are packages available now that were invented by physicists and published in the peer review in the last couple of years. And those packages do exactly that. They've devised these packages for the purpose of looking at what happens when matter falls into black holes, how a black hole forms during stellar collapse, what happens when you go on the inside of the event horizon of a black hole, and the production of gravitational waves from a black hole as matter falls into it. So that package is actually the kind of package we need, and we've got that package, and one of the next things we're going to do, probably about 2 years from now, is begin high-powered supercomputer numerical algorithm simulations to do visualization of how a warp looks when you try to build it. And the last important thing is lab experiments using what's called simulation or analog gravity. It's where you can do gravity on the tabletop in a laboratory using electromagnetic radiation, and what you're using are metamaterials. You're going to use metamaterials to reshape light, and you're going to reshape light in ways that will reproduce the effects of a warp drive or a wormhole. They've already been doing similar effects like that with sound waves to study black holes. And they're also doing that with light waves now to study black holes using a simulated experiment. Instead, you're going to create space-time in the lab, and you're going to bend that space-time. Only that space-time is not real space-time, it's electromagnetic radiation. Electromagnetic radiation can be treated like a space-time. It can be curved and manipulated and bent like a space-time. So you can get it to behave like a black hole, or the planet Earth, or a rotating mass, or a warp drive in a wormhole. And so you use metamaterials to shape the space of electromagnetic light, electromagnetic radiation going around the metamaterial to create the effect of warp drives and wormholes. And that is pretty much the whole thing, I think. So is this going to be our future? That's the question. Thank you. Okay, do the questions over there. Yeah.
All right. Thank you, Dr. Thank you, Dr. Davis. Is this on? No, thank you. I can't even hear. Thank you, Dr. This is going to be one-on-one, so feel free if you have any questions just to make your way on over. We don't have time for a microphone.
How you doing? John, good to see you. Yeah, yeah.